see if I can function well enough to do this on this little iPad screen. If not, I may get frustrated and quit, so hopefully I can hold out for Morgan and Virginia to be able to have something to go by. All right, 42, yes? Really? Yes. The base of the solid is the disk x squared plus y squared less than or equal to 1. Okay, which would make a what? A circle. Okay, so we have a circle centered at the origin and all the points enclosed, which forms the region, yes? All right, and then it says the cross sections by planes perpendicular to the y-axis. I'm going to guess right there that that might be your problem. Did you do everything in terms of y?
I don't know, I erased everything. I erased it like 3 times.
Okay. Well, if you had...
Yeah, I was doing it.
Okay.
No, I don't know.
Okay.
It might have been in terms of both, and it was just switching back and forth. Who knows?
Oh, I won't even ask how that would work, but perpendicular to the y-axis between y equals -1 and 1 are isosceles right triangles with one leg in the disk, as pictured, right? So basically, what structure on the triangle is related to the circle? One of the legs, right? The base of the triangle? Okay, so we're talking about a triangle here, so we're going to do 1/2 the base times the height. And that would be your geometric formula you're working with, right? Okay, well my job is to come up with an A of x. So that means that the circle runs from the vertex at the right angle and the vertex of one of the other angles at the end of the leg, right? Okay, how could I express that? If I use a top minus bottom approach. But now I have to think in terms of y, right? Well, they gave me the equation in terms of both. They didn't baby me and solve this one for me, right? But when the whatever the cross sections are perpendicular to, that's the variable you should be working with. So when the cross sections are perpendicular to the x-axis, you're going to use x. When the cross sections are perpendicular to the y-axis, you're going to use y. And I don't think I specifically stated that in our prior discussion of this. All right, so if I want to take x squared plus y squared, and I want things in terms of x, what does that mean that I need to do? Solve for y, right? Okay. Or no, I don't. I solve for x. I'm sorry. I'm so used to saying y. Right? Are you with me? Okay. So I'm going to have y's on the right where I would normally have x's, yes? So I have x squared equals 1 minus y squared. And then what? X equals the square root. Now, we actually, in this case, have the plus or minus, don't we? Because that's the definition of the shape. So we want to treat this as two different functions. Well, if I'm thinking relative to the y-axis, and if you orient yourself thinking like you're standing with the y-axis in front of you long ways, like you're used to having the x, right? What's top? The positive one, yes? So it would be the positive one minus the bottom one. I'll make sure that's not my phone making noises. I don't think that's one of my sounds, but we'll, I don't interrupt you. Okay, so my top minus bottom. Now let's think, and I want you to think this through as opposed to writing it out just to have less to write out. So what would that wind up giving me?
2 on the square.
That's right, 2 on the square root of 1 minus y squared, right? Because it's minus negative, yes? Okay, so then my,
That's our base?
yes. So the base of this triangle is equal to 2 square roots of 1 minus y squared. Does that make sense? All right. Well, now, I was going to say, but now we got to come back to the fact that for the area, the geometric area, so if I'm trying to arrive at 1 times base times height in terms of x, well, so far I have 1/2 times 2 times the square root of 1 minus y squared as my base, right? So I got to think about my height. And it's isosceles, which tells me what? The legs are congruent, right? So that means that it's times another, wait, I got to not leave my 2 off. 2 square roots. Oh, wait. Yeah, that's right. Never mind. So there we go. right? Okay, well then, that little half takes out the first two, right? So then I'm left with 2 times 1 minus y squared. Yes? Because I would pull the 2 out and then multiply the square roots times each other and the square root will go away, right? Okay, well then my a of x, or not a of x, tell you what, you get in the habit of thinking about x all the time. It's hard not to stay there. All right, a of y equals what? What we just wrote, right? 1 minus y squared. Simple enough? So then my integral, or to find my volume, that's going to equal what? The integral from -1 to 1 of 2 times, in fact I don't actually need parentheses because it's all multiplied, and I would actually pull the 2 out front, but I didn't leave myself room. 2 times, this, not the square root, I keep wanting to put the square root back on it, 1 minus y squared dy. And then it's pretty straightforward from there, right? I presume the hard part of that was getting it set up. Does that make sense? So did you feel the steps happening while we did that? So the very first thing you got to figure out when you have these cross-section problems is what the relationship between the cross-sections shape has with the base. And that completely depends on how it's described, right? So then once you figure that out, you have to figure out how to translate from the geometric version of the area to the appropriate variable representation of the area, and then just integrate. Make sense? All right. Anything else? Are we good to move on now? Okay. I want to get you thinking in terms of how the rest of the volume problems work, okay? And if you see, and let me just tell you how you're going to know where you're going, which method you're going to approach this with, okay? If you see any form of the word revolve, okay? So revolved, revolution, any of those words, then you're going to be using the technique that we're about to do. Okay? That's how you know you're in the other version of volume, because really there's only 2 that you're going to have to know. And there's a method called cylindrical shells, which I have nicknamed the Cousy method, which you probably, if you take calculus in college, you will learn it. It once upon a time was an AP concept, and they removed it from the list a decade or so ago. So I decided not to teach it anymore because I thought it was really straightforward, but it blew the minds of the kids that I was teaching at the time when I tried to teach it. I will tell you, the problem you had, and I think it was in 8.2, where it said that they gave you a population density formula for a city, and then they told you to think of one of the strips around the city, or, like the rings that would be formed by using circles as a rectangle. It's kind of that's sort of supposed to set the stage in your mind for cylindrical shells. So if you plan to go into any kind of math or science type degree program, or anything where you're going to take calculus in college, you should probably, in your Chapter 8 summary, include that example in detail and draw some pictures there, because basically cylindrical shells is sort of a 3D approach to what we did there. Okay? But for us, we just have to know, so the magic phrasing of what you just did in the first part of 8.3, what we just went over, is going to be the cross sections are circles or squares or rectangles and so on. Okay, so if they describe a cross section, that's the technique we just learned. So you're going to need to know that little process that I just outlined, and that is the first thing that's on your blue or green sheet, whichever color you picked up. Okay, so that little 4-step thing that we spent the first part of 8.3 on. Everything else on this sheet is how you handle it if the word revolve or some form of it appears, okay? Now, to get you thinking in how this works, I'm going to sketch you a little picture here, okay? We're going to stay, once again, just for simplicity's sake, we're going to stay in the first quadrant. All right. Now, don't panic, but this would be, in essence, if I had to write a function to represent what I'm about to draw, it would be a piecewise function. And we're going to go from 0 to b. So our first x value is 0. Our ending x value is b. So if my limits of integration were from 0 to b, b being any positive number, then let's put a little vertical line, and this is kind of working very backwards, but put a vertical line there, which tells me where I would stop for my integration, right? Okay, well then, let's come back to the y-axis and draw a little line segment there with a negative slope coming to slightly away from the y-axis, okay? And then from that point, let's make a arced curve that comes over and meets that vertical line. All right? Got that description in your head, Neil? Did that make enough sense for you to follow? Neil?
Yes, sir.
Okay, you're with me?
Yes, sir.
Okay. All right, so I'm gonna color this green for emphasis, okay? Now, what's the significance of the blue colored line? That's just where you're going to stop, because y'all had some of those where the function itself didn't stop there, but you were given limits that you're looking at, right? Okay. Same idea here. Now, what would happen if I took that shape, just that little line segment connected to that sort of parabolic curve there, and rotated it out of the picture towards me, thinking in 3D, around the x-axis until it came back to where it was? What shape would be formed?
Peppermint wrapper.
Peppermint wrapper, okay, that's interesting. And you said a circle?
A bullet. A bullet.
A bullet?
Like one of those
Looks
pin
kind of like a
fish.
fish.
Yeah, like a
One of
fish.
those-
Like a fish.
Or
Taylor
like
bullets
a
we
shrimp.
were in GRTC. They look just like
No,
that.
a big
Wait, I can't find it. I don't know where it is.
Yeah, that's what
It looked like a nuke. It would look
Wouldn't it look
it
like
like
a
a doorknob.
Wouldn't it? Okay, there's a lot of ways you could describe it, but do y'all see the 3D image in your head? Okay, and I had my vase here somewhere, but I don't know if I took it home or it got buried in all the junk in my closet. But you know when you go to the grocery stores and Walmart and places like that that have the live flowers, and there's always those little fairly cheap little clear glass vases with the standard lip around the top edge, and then the bottom is sort of a rounded, right? And the vertical line here, if we made that part of our rotation, it would make the base of that, right? Okay, that's what you're going to get, all right? Now, imagine that that's solid, though. Because if I integrated the shape, wouldn't I get the area under it? So if I'm rotating that solid, it's not just going to be a vase, the inside's going to be full, right? So it's a solid, so imagine you've cut it out of wood. So it's sort of a vase or whatever description made the most sense to you. Shape. Got that in your heads? All right, well, let's say we're going to take that and slice it so that my slices run perpendicular to the x-axis. So I'm going to slice it like right through here, this way. I'm going to cut it up into a bunch of slices. If I cut those up into a bunch of slices, and I pick one of the slices up and turn it so that I'm looking at where the center, where the x-axis would be pointing at me. Where would that center be? I mean, that point be? That would be, the x-axis would be the center of this object, right? Because that's my axis of revolution. Does that make sense? Okay, well, if I take that slice and turn it so that I'm looking like, and it looks two-dimensional, what is my shape? A circle. Okay, so if I have a revolution shape, what I'm going to get is circular cross sections. Fix that because that looks really terrible. Does that make sense? All right. So if this were a known cross-section problem, how would you approach it? Okay, now that I've just told you, all of these are gonna be circles, so if I had to approach it like an area problem,
Area of a circle.
Pi r squared.
I'm gonna start with pi r squared, right? And then what's my job? Okay, well, if it was this problem, let's just say, let's call the name of this green function, this little section that we were revolving to create this shape, let's call this f of x. F of x is the function I was revolving, all right? Then what would f of x give me for my circle?
Wait, can you say it?
What would the significance of f of x be to the circle? What's the circle? It's the cross section, right? The slice, yes. So when I'm looking at a slice, what does that circle have to do with f of x?
Give you the thickness, like on that.
It gives you like the outside shape.
Okay, y'all aren't thinking about thin enough slices. Have you ever gone to the deli and ordered meat and had them slice it for you? Or been with somebody or walked by and seen them doing it? Okay, sometimes they slice it really, really thin. Why, as calculus students, would we want them to slice it really, really thin? That's right, because the more slices I have, the more accurate it is. And when we take the integral, how many slices are we getting?
Infinite.
An infinite number. That's the best case scenario, right? Okay, so think of a super thin slice. Think like a 3D printer, because I'm sure 3D printing came from this idea. Do you know how 3D printing works? It literally puts another little tiny layer of plastic or whatever material it's using to create the shape. So if I take a really thin slice of this solid object, which looks like a vase from the outside, but it's full, the inside's not hollowed out, and I take a cross section, you agreed with me that would be a circle. It's a very thin circle. So tell me, thinking like an 8.2/8.3 student, what does that give me for this shape? The radius, where f of x equals the radius for a equals pi r squared. Now let's just say this was a piecewise function. I'll push it just a little bit further, and I know it's Friday morning, but this is a very important lesson to understand, because I don't know if you noticed when you took the diagnostic exam how many times the volume questions came up. That's how many times they're going to come up on the actual exam too. So this is a very important idea that we're closing out and in on at the same time. But if I had to define this function in pieces, clearly the pieces would occur where it goes from being a line segment to being that curved segment, right? Okay. So if I had to do this thinking like a calculus student, then my first job would be to figure out where that break is, right? Well, assuming it's piecewise, that should be obvious, right? Let's say that's from 0 to 1. Then I would integrate from 0 to 1, where my radius would be dictated by the equation of that line, right? And then I would integrate from 1 to b, where whatever the equation is that gave me that parabolic shape becomes my radius, right? Because what my radius is depends on where I am on this piecewise function. Does that make sense? All right. So that's kind of the theory behind what we're doing. All right. Now, look at the front of your reference. It's the first thing that comes after what we've already covered as far as the known cross sections. So this is called the disk method. Do you see the disks? Where did the disks come up in what we just said? That's our cross section, right? Now notice the title. This is the volumes of solids of revolution. So there's really just two methods here, but in a way there's three methods here, and we'll get to that in just a minute. All right. So volumes of solids of revolution of one function. All right, so let's stop and do one of those before we do one of the other types, okay? Well, but before we do, and notice I give you both the X and Y version. Y'all see that? And then what is R of X in there? That's the equation. That's my function of revolution, right? That's whatever function I'm revolving. Does that make sense? That establishes the radius of my circle. Do you see the pi r squared in your integral there? Why is the pi pulled out? Because that's what we do, right? If it's a constant, we pull it out. All right, and a to b in our picture would be 0 to b, right? Okay. All right, so before we go to the other version of this, let's go to a basic example of how this works. Let's start with number 8. And I would feel worse about starting with number 8 if we hadn't just started our conversation by talking about the one from the first part where we were in terms of y. So this will be good practice for our in terms of y, because I want you to get less intimidated and more comfortable with that idea. All right, so find the volume of solid generated by revolving the shaded region about the given axis. All right, well, they were kind enough in number 8 when they tell us that we want it about the y-axis to give us our equation solved for x, right? Okay, so now, and in these pictures, they'll draw like one little line segment. That little line segment represents one slice, so that you can get an idea of where your cross-section would be. All right, well, if I took that triangle and revolved it around the y-axis, what am I going to get?
Upside down
A cone. It's a cone, right? Not a pyramid. Pyramid has corners. This is just going to be, if I just revolve a line, think about it. Take your pencil and draw and do that for yourself. If I rotate that pencil, and it's going to be, what's going to make the point? It's where it crosses the axis I'm revolving around, right? Do you see it? I'm going to get a cone. Y'all with me? A solid cone, right? Okay. So we are going to integrate. If I want this volume, let's see if y'all can't jump in here anytime now.
From 0 to 2.
Y'all agree with her or not?
Yes.
Okay. I heard 0 to 2 and 0 to 3.
0 to 2, because we're going on
because we're doing it in the y-axis.
Yeah, so I need my y's, right? And that's why I let y'all do that, all right? So I know, now that we're dealing with circles, it's almost like a shortcut to what we were doing before, because I don't have to stop and figure out what the shape is and all that stuff. It's pretty much going to be fixed that way. All right? So I'm going to put my pi out front, integrate from 0 to, which one is it? 2. Everybody see y? Not y, but y. Right? Okay. Y'all are a tough crowd. Okay. But it's a tough life, so I guess that's good. You said it wasn't funny?
That wasn't funny.
Oh, it was a funny. I'm glad you identified that for us. Okay. Because not everybody found it, so. All right, so now what do I do? What's my radius in this picture? 3y over 2, a.k.a. 3 halves y squared dy.
So you couldn't just pull your 3 halves out.
Well, clearly you can, but you can't. It's not just 3 halves. Why? Because it's inside the square. That's why I couldn't just throw that out front, right? Because my radius has to get squared before I deal with any constants. So now, what am I going to pull out? So I'm going to have 9 pi over 4. And I'm going to jump right to the chase here. We're going to anti-derive by looking at it. Y cubed over 3 from 0 to 2. And before I even start integrating, what should I do about that 3?
Pull it out.
Nope. Let's knock it out and turn my 9 into a 3. Right? Okay. So then that gives me 3 pi over 4 times 2 cubed minus 0 cubed, which is, oh wait, I don't put the equals there, I didn't put the parenthesis, which is equal to 3 pi over 4 times 8 over 1, 6 pi. I don't think y'all can see the other side of the pie, so I'll do that.
This
Pretty-
is easier than the one that we learned. So is it always going to be a circle?
Can you think of a way to revolve something where the cross-section wouldn't be a circle? The answer to your question is yes. It's always going to be a circle when it's created by revolving something. By definition, a revolution, it's going to stay a fixed point based on whatever my function is.
All of these intersections in circles.
Becca's like, that's just too good to be true. I can't wrap my head around it, so I'm going to just ask if that's what it is.
Like one of those swirly pasta noodles. Is that not a revolution? Yeah.
It's not a it is a in a sense a revolution, but if you think about it, that would be,
It's not on that the same thing.
yeah, it's not relative to the same point, right? Because it's circular. Basically, that would be like taking the wire off of your spiral notebook and revolving a shape around that spiral. Right? In the context of what we're talking about. Okay. So, let's pick another. Let's jump down to number 12. And in this set it says, find the volume of the solid generated by revolving the region bounded by the lines and the curves about the x-axis. Okay? So you've seen one where you're given a picture and how straightforward that should be. And now we're going to get one where they don't give us a picture, they just give us our functions. But the good news is they've allowed us to stay with respect to x this time. And it's a good old friend, x cubed. This is a no calculator question because you should be prepared to handle this. All right? So from y equals 0, x equals 2. All right? So if we know we're in terms of x, the first thing you're going to need to do is to draw a picture of what you're revolving. Okay? Well, if I'm going from y equals 0, at y equals 0, okay, this is bounded by the lines and curves. So that's where y equals 0, what is that? X-axis, which is a fancy name for doing kind of what you're used to doing anyway, right? You with me? All right, so I'm between the x-axis, and I'm only going to go to 2. So I'm going to do a super zoomed in picture of what I'm doing here. All right, do y'all see why I only need the first quadrant? Okay. All right, because x cubed here lives in this first quadrant, right? And I'm going to just draw what looks like a chunk of a almost parabolic shape that would be the right side of the cube, right? So we're revolving around the x-axis. So what would this shape look like?
Like
I like a skating rink.
Like a cup? What do you mean like a cup? What kind of cup?
Because like there's gonna be like a hollow middle, but like the outside's gonna be like.
Well, remember all these are solids.
I think it's gonna look like a mountain.
It's gonna look like one
Like
of those.
almost like a skateboard.
Oh
like,
wait,
if
never
you
mind.
put,
No,
like,
I'm thinking
it's
about
gonna be
it.
like this.
I'll see
and-
you.
Right? Almost think like the
Hershey Kiss.
like the front of it.
You
Well,
know those little things that you spin like you do
A
like this,
Beyblade.
and if you cut it in half, that's what.
Yeah,
They
like
have-
top. The spinning
Yeah,
top.
she spinning top.
Oh,
Okay.
yeah, those are spinning top.
well, this would be almost. It would be like a cylinder, but with rounded sides, right? It would come to a point.
Are you going around like the?
X-axis.
Okay. So would it kind of be like a cone?
Yeah. What did I say? A cylinder? I'm sorry. My brain is tired. Yes, a cone. Like a cone with rounded sides. No wonder y'all were looking at me like, what are you talking about? Yeah, this is, I was like, God, I thought they had it. And then y'all looked at me like that instead of saying, do you mean a cone? Thank you, Marilyn. Yeah, this looks like a cone with rounded sides. Almost like a witch hat that's,
Yeah, which
you see what I'm saying? But without the brim? Yes?
I can see Hershey Kiss.
But, okay, Hershey Kiss would be like a melted version, sort of, yeah, because it's more rounded. This is, your concavity's in the wrong direction. Right? Okay. So y'all with me now? Because it's kind of helpful to think about that, just to imagine. Now, I will also tell you that if you have trouble thinking in 3D, if you do a little bit of searching on the internet, there's a lot of interactive sites where you can watch the 3D shapes be formed by this. Okay? So you might want to just Google solids of revolution and see if you can find some interactive sites that way. Okay? And if you can't, you can look on my class page has some links, but I haven't looked at them in a while, and every once in a while those links just kind of go away, so just be mindful of that. All right, so here we go. So what's my job to do? All right, so it's pretty simple, isn't it? So my volume is, what's the first thing I'm going to write every single time? Pi. I'm going to write pi. I will tell you, one of the most common errors on this part is forgetting pi. And you might even write it on every step, but then you'll do all the computation to get the numeric part over there, like the Roman numeral part. Not Roman numeral. Oh, my God. Like 7 or 27 or 842. And then you go, oh, the answer is 842. And then, nope, it's 842 pi. And especially if the answers in the back of the book are in decimal form, that might be less obvious for you. But like if you got a whole number answer and go to the back of the book and it's a decimal, it's probably because you forgot to multiply by pi. Okay? Just keep that in mind. All right, so we're going to iterate from where to where? 0 to 2 of what? x cubed squared dx. Because x cubed here establishes my what? The radius of revolution. Make sense? All right, so then we're going to write the next step, and we're going to jump straight to our brackets. So I'm really integrating what? X to the sixth. There's your exponent properties coming back to bite you. A power to a power, you multiply. X to the sixth. So this is x to the seventh over 7. From 0 to 2. No calculator. Don't panic. All right, I'm going to go ahead and pull the 7 out and put it under pi, so that I can do 2 to the 7th minus 0 to the 7th. All right, well, it's really simple though, because 2 times 2 is 4, so that's 2 of them. 2 more, so it'd be 4 times 4 is 16. Times 2 is 32. Times 2 is 64. Times 2 is, there you, 120 what? Yeah, so this is 128 pi over 7. Good?
These get harder.
Nah.
This week, I have a question.
See?
Like, I was doing some stuff last night, and then I guess maybe I just got confused. Like, I was thinking about it too much, and I just got myself confused. So say if you had, whenever you did your brackets, or even in your intervals, say you had like if that was like a 3x to the third plus 2 something, like, and you had like a few coefficients, could you bring all those out to the front? Because I was getting confused, because then it would times it by the whole thing, but.
Okay, if I have, let's say I had a constant pulled up front, and then my integrand was a product where I'd factored something or brought in different factors, especially on that section where you're bringing in stuff to represent different parts of a shape or something. If I had something like 2x plus 3 times 3x, then the first thing I always tell you is what? Do the algebra first. If you have a plus or minus involved, you can't do that. But if I had something like 2x squared times 3x squared, or 3x to the fourth or something, then I can multiply those two numbers together and pull them out and multiply them by the constant on the outside. Yeah, you want to get all your constants together and rake them to the left where you can.
So even if you have like a constant with like an x here plus like another constant with like an x squared.
No, if there's pluses, you can't do that. The only way you can do it is if you factored it out. Right.
Okay.
If it's factors, if we're looking at factors with multipliers, you can pull the constants out. But if one of my factors is something like 2x plus 3 or 3x minus 1, I can't, because that 2 or that 3 only goes to the variable it's attached to, not that whole expression.
Okay, that's what I was thinking, because I was like, oh, let me just pull it all out, and I was like 60 times this whole thing. I was like, that can't be right.
Well, no, that could be right, but that's not right if that's what you were thinking. All right, now we're going to switch it up a notch, because there's one other type of problem, because it's one other type of problem, and that's it. You've kind of seen everything there is here. All right, let's just say, let's go back to my original little sketch that we had. Same idea. All right, why, when I rotate this shape that we've agreed would be sort of a vase shape for the sake of discussion, everybody okay with that? But solid. Why was that solid? Because the integral, and that's the way to think about it. If I took if I just wanted the area of this, I would take the integral, right? So if I take the integral, I'm getting not just the line itself, but all the space between me and the line if I'm on the x-axis, right? Okay. Well, let's just say that instead of having just that, so wait, let me come back and label that one, because we called that f of x in the first instance, so let's keep that our f of x. All right? And then let's, and I'm going to back up and put a white line to represent our ending spot there. That probably doesn't show up as well. Let me put that in pink. Isn't today pink out day? Can't really tell it looking around this room. I just don't have enough pink to... Oh, wow. The shame I have brought to this room, right? Okay, well, let's just say I come under that shape and throw in a line that starts at the y-axis and falls to the point where my B where x equals b is 0. So we're at the point b0, and that's where my little slanted line I've drawn inside the base comes down and meets b at the x-axis. Okay? So let's call that, be really creative here and call that g of x. All right, so if we revolve just f of x, we get a solid closed shape, yes? But let's just say, then in addition to that, we're not just revolving the f of x, we're revolving the region bound by these two functions. How does that change my shape?
You'd have to find the area of both pieces and then subtract.
No, I'm not asking you for the calculus. That will lead you astray. I'm asking you what this shape looks like.
It was just like the cone is like taken out.
That's right. It would be like they cut a cone out of our vase, right? So we've still got that solid vase shape we had, and somebody cut a cone out of it, right? So now if you put flowers in it, they're sitting in the cone, right? Okay. One step further. Everybody got that in your head? All right, now I'm going to flip that new shape, which is now not just a solid shape. It actually could be a vase, right? In fact, I've seen some funky vases that kind of look like that. If I took it and sliced it sideways, what would my cross sections be now?
Sideways, like,
There's literally circles where they have holes in them.
It would be like this.
That would get,
Like a
yeah,
CD.
it is.
Yes, they would be like discs, like a washer,
Yeah.
right? It'd still be a circle, but it's going to have a circle cut out of it, right? Like a CD. Y'all remember CDs? Okay? Y'all make fun of your teachers who remember 8-track tapes and such as that, and you're going to be like the old people someday. They're like, what's a CD? Yeah. Oh, sorry. Get the back of your sheet. That's where we're going now. So now, this is the washer method. And it's not like the washing machine where you wash your clothes. This is a washer like out of your daddy's toolbox. Or your mother's. What's the difference in the title there? Besides the washer versus disc. Two functions. So if I have one function, and to me it helps if you stop and think about the shape before you start, because if your shape has a hole in it, it's a washer. If it doesn't have a hole in it, it's a disc. Okay? Now compact discs, the CDs, as Clark pointed out, have that hole in the middle, right? But a disc, technically, by definition, is just a circular slice of something. Okay? It's a flat. Does that make sense? Okay. Yeah, like a frisbee, without the curves.
Nope, I got those frisbees that have holes in them.
You know, slow it up. I'm slow it up. We can design a base now. And like tell you how much is going to fit in the base. And how thick the outside
Yes.
is gonna be.
See how smart you are? It's amazing what y'all have learned since you met me.
This is our accumulation.
All you have to do is just
All right, so let's look at, oh, not in yellow, because you won't be able to see that very well, I don't think. Let's look at number 18 from that same set down there. Now we have y equals 4 minus x squared, and y equals 2 minus x. All right, so my first job is to figure out what this region that I'm revolving looks like, so I can think about it, all right? And we're still revolving around x, because that's the set we're in, okay? So my first job is to do what? Draw the picture, all right? So 4 minus x squared is a what? An upside down parabola. Where is its vertex? At 4. And where would its 0 be? This is the difference of two squares, guys. It's 2, right? Okay? And then 2 minus x is in slope-intercept form, yes? What's my y-intercept? And my slope? -1. All right, so I'm going to be stuck in the first quadrant with what I'm revolving, right? But the good news is everything I'm showing you works no matter what quadrant you're in with the region they describe, okay? All right, so I'm going to go up 1, 2, 3, 4, and then 1, 2 to the right. I didn't really make this big enough, but we'll go with it. There's my parabola. Then I'm going to come back, put my line in, and it goes down 1 from 2, right, down 1 to the right 1. It's going to be somewhere in there, but I want to know where it hits the x-axis, so my picture's pretty accurate. Where would it hit the x-axis? 2, 0. Wow, that looks kind of like what I just gave y'all on that other one, doesn't it? And I hadn't even looked at this one. Hopefully that's a sign of good things for my day. All right, so there's the shape I am revolving around the x-axis. What would this one look like? And if you have trouble seeing these, think about what it would look like from the outside. So like if it's flipped upside down and you couldn't see the inside, what would you see? A bowl, right? It would be a bowl with a fairly unstable bottom probably because there's no flat surface there for it to sit on. Okay? And then when I flip it over, what would I see? Right, I'd see a cone cut out of the center, right? With fairly thick sides. You with me? All right. So which method is this? It's the washer. So that is the back of your sheet. Okay? And notice that I gave you everything in terms of X and Y. And you know how we've been doing the top minus bottom? Now you should start thinking outer minus inner. And that becomes important in just a moment. And we will talk about that. Okay? All right, so let's go ahead and do this one real quick, and then I think we can do one more, and I can let y'all try some. All right, so my volume is going to be what? Definitely going to start with pi, because we're revolving, right? From 0 to 2. Stop anyone who speaks from moving forward if you disagree, okay? So if I hear nothing, we're going to move on.
The first time you do the 4 minus x squared, quantity squared.
Can we just?
Okay, well, okay.
Together?
Okay, what is my outer minus my inner? I mean, what is that? Okay, what would that mean, outer minus inner? Well, first of all, what did top minus bottom mean? Which one is the furthest above the other relative to x-axis, right? Well, we're still doing the x-axis, right? So what's on the outside of the revolution if I'm standing on the x-axis? The 4 minus x squared, right? Now, what does this sheet tell you? Because let me take you one step further, because I think some of the questions that I see sort of bubbling in your heads will go away if I ask you this. All right, back before we got to 8.1, how did we find the area trapped between a function and the x-axis on a region? You integrate from whatever the a to the b is, right? Because that gives me the area between the function and the x-axis, right? Well, then in 8.1, or was that 8.2? No, 8.2, where you did areas in the plane, then you had two functions, right? How did we get the area between the two functions? Top minus the bottom, right? So now, when I'm in thinking 3D, well, you're still standing on the x-axis, but imagine that function going all the way around you, right? That's how you got to think about your outer, right? Well, if I just integrated the outer function, what would I have the volume of?
The entire.
Everything, all the way to me, right? Well, then somebody says, wait a minute, let's go in and put another one in, but it's going to make a space for you to stand in. All right, so it puts that line in. How could I figure out how much volume that took out? No. If I just want the volume of what I took out, I would just integrate the inner, right? And how would I get the net result? I would take the original integral of the outer and subtract from it the integral of the inner. Look at the formula on your sheet and tell me why that's what that's really doing.
Wait, what's your question?
Look at the difference in the two formulas and tell me why they're the same.
Because everything's identical except for your
the same interval.
Yeah, you're on the same interval, and our properties of integrals allows us to go from separate integrals, which is what I just described, right? To our other version. But look closely at this, because I have a feeling another common error is going to occur. What do you have to keep distinct? The functions as squares, right? Okay, so my outer, we agreed, is the parabola, right?
So I have a question.
Okay.
So what about that piece that's it past the y-axis in that function? Where it's still.
No, because it's specified that I'm looking for the volume of the solid I get when I revolve the space between them. And these intersect at the x-axis.
Yeah, but what about the part past the y-axis? That where they extend, like, because the line's still under that curve, past the y-axis. Or we have to stay in the first quadrant for these.
Yeah, but it said. I'm having to think about how to answer your question. Find the volume of solid generated by revolving the region bounded by the lines and curves about the x-axis. So we're revolving around the x-axis. But you would, in order to actually find a definite integral, and looking at what you're saying, and I almost hesitate to draw this, but I guess I'll draw it on there and then take it back off. So don't put this on your paper for the sake of avoiding confusion later. So, Marquise, let me make sure I understand what you're saying. So you're saying if this line keeps going, and this line keeps going.
No, I'm talking about the other way.
Across the y-axis.
Until they intersect.
Until they intersect again, like, so we,
In the second, I think that's the second quadrant.
in the second quadrant.
Yeah, it would be in the second quadrant. Oh, yeah. Okay, I thought you were talking about this part down here. Okay, I'm glad I drew this picture because I was not understanding what you were saying. So, oh, that's a fair point. Let me ask you a good question now that you've brought my attention back to what we're doing. Can I use symmetry?
No.
Why not?
Because of your line.
Because I actually need to extend it back there. And then the parabola would be coming down reflectively on the other side, right? So I don't have symmetry. So what's that? That's going to change one thing about what we're doing. What is that one thing? And so, and how is that going to change the shape we had in our heads? Now it doesn't have a flat top. It comes like it's curved back to the top, right? To the cone. Does that make sense? So it'd be rounded on the outside, flat on the inside still. Y'all with me?
Wait, so are we including the second quadrant?
Yeah, we have to, because it did give us a limit there. I was thinking it said 0, but I was thinking about the last one. That's why I had to go back and reread it. So what will that change?
Your limit.
Our limits. So we're not going from 0. So we got to back up. Erase your 0. Let me see if I can do that without such. Okay. How do I figure out where that is? Oh my God, did you just say plot points?
You got
Yeah, set
7
them
equal
equal,
to each
like
other.
7 equal to each other.
Set them equal to each other. 4 minus x equals 2 minus x. -1. Do we agree it's -1? Okay. That's a very low-key agreement. But I'm going to run with it. If you turn out to be wrong, you're all in trouble because you sat there and let the people who spoke speak. All right. I'm not saying they're wrong. I'm just getting frustrated with the same people who never, ever make a contribution here. So I guess I should go back and shade in that little spot too, so that our picture actually represents what we're doing. All right. So far, so good. We got pi times the integral from -1 to 2 of, and that's not a bracket for an integrand. That's a bracket to denote what I'm about to write. What is my outer function? 4 minus x squared in parentheses squared. Right? Yes.
Right, this might be a dumb question. How do you know that you would shade that little piece up top? Right?
Because it didn't give you a limit. We want the area bounded by the two functions.
Yeah, I know, but how do you know that it wouldn't be what's under that line?
Because it's not bounded by the functions. Bounded by the two functions. If it's bounded by this parabola and that line, it has to be the space
the
between.
parabola has to be a point.
Yeah, you with me?
Yes.
Okay. And no question is stupid when you're trying to understand what's happening. Y'all need to be asking these questions. That's why I get frustrated that it's the same 5 or 6 people asking those questions every time. Okay? And you're just sitting there waiting on the off chance somebody's going to answer the questions going through your head. That's kind of like me waiting to win the lottery. Not a good plan. All right, so now what? Minus 2 minus x, the quantity squared, bracket dx. Right? Now, if you haven't already gotten in the habit, you need to get in the habit now of doing the algebra first. And this is where your weak algebra, because you were too lazy to take my advice last year, is going to come back to haunt you. Because you need to get fast at this, all right? I'll answer it. Very quickly write the expansion of those two binomials without having to pull it out. Yes, ma'am? I don't have a second, so. Okay, I should be able to check it and send them to you then. Alright, okay, bye.
That sounded so weird. All I was-
Ms. Stu was trying to be very polite and apologetic about interrupting me and then said, if you could just check your email. I'm like, I can't do that right now. Sorry, I'm teaching. Apparently that's a pretty foreign concept around here. All right, what is 4 minus x squared expanded? 16 minus 8x. Oh, no. What? What? Minus 8x plus x squared. Oh, my bad. I was like, what are we talking about? I didn't even look at it. I forgot it was the squared. So sorry. I should have known if Haney was saying it was right. Shouldn't I, Haney? Okay, so this is what? Plus x to the 4. There we go. That's better. I'm sorry. Miss Du threw me completely off of the planet here because I'm still thinking about why. No, I let my tired brain go off on tangents when this sort of thing happens. All right, so that's the first one's expanded. Hopefully the second one went better. So we're going to have, and I'm going to put that in parentheses for emphasis here. What's this one?
4x plus x squared.
Yeah, Miss Du stole from me the opportunity to call you out if you couldn't do that. And there's a DX hiding back there. I ran out of room, okay? Because I was going to do that super fast and check you on it. That's how fast you want your algebra to be. Because if you're having to do the algebra piece by piece and think about every term, your brain is going to be really tired by the time you finish the AP exam. So get better at that. All right, so this is the integral from -1 to 2. And I'm probably just going to do this and stop and not actually go to the end because once we get to this step, you surely should be able to finish the problem. So when we combine our constants, and I don't care what order they're in because I'm going to plug constants in back for my A and B once I hand it arrive. You know what I'm saying? All right, so what constant will I have? I don't know what I was doing, sorry.
It's 16.
16.
I'm sorry, me and this thing are arguing for a minute. Okay, try again. So we're going to have 12. And then we're going to have
Yeah, minus 9x.
minus 9x squared. And then plus x to the 4th.
Minus x squared. Wait, minus 4x.
How about plus 4x? See how that distributing that minus messes you up? That's another little algebra mistake. So for those of you that got that wrong by looking at it, here's what you need to do. You need to say, okay, well, if this is a minus, I'm going to turn it into a plus and change the sign of everything in there.
So wouldn't that be a minus?
It's plus 4x. It was minused, so I turned it to a plus because I was minusing a minus. As I said, check those red marks, Marquise. All right, so y'all, you see what I'm saying? That should be pretty straightforward to go from there, yes? All right, so to move on, because there's one more thing I definitely need to show you before I go check my email and see who needs to go see Miss Du. Probably Verge and Morgan are both on the list, I'm guessing, just because they're not here. And probably Matthew Gallahorn as well. Well, shout out to all my absent peeps. All right. Ah, yes. Here's what I want. Number 22. It says in 21 and 22, find the volume of the solid generated by revolving the region about the given line. We're not revolving around the axis anymore, kids. Number 22 says we're looking at the region in the first quadrant. Now see, that wording tells you we don't have to worry about anything else, even if an intersection happens outside the quadrant. You with me? So you have to read it and draw the picture as it's described, which I gave you a counterexample of how to handle that by not actually reading it more carefully on the last one. So we know we're in the first quadrant, so I'm going to go ahead and sketch a first quadrant. And it says bounded above by the line y equals 2. So I'm going to put a line across the top of my picture and label it y equals 2. That's my upper boundary. Below by the curve y equals 2 sine x. All right, let's think for a second. What does the sine graph do at the origin? Does having a 2 in front of it change that? All right, and then it would peak up, yes? And if the 2 wasn't there, it would peak at 1. But where's this one going to peak? Okay, so I just want to draw my 2 sine x. So I've got y equals 2 sine x. So this way I am sketching and recording the functions involved, right? And here's what's cute, which I want you to tell me why they could have left this out. If it said it was bounded by these 2 curves in the first quadrant, don't we already see the region? But then it gives you the closed interval from 0 to pi halves. Why is that redundant? Because that's exactly what we already drew. Do you see the power of drawing the picture? Because then that should make you say, yes, I did it right. You know what I mean? So if you learn this process I've taught you since pre-cal about recording what you know as you know it, then it will guide your thinking. All right? So here's the clincher. And then it says on the left by the y-axis, also redundant because it said in the first quadrant, yes? Just saying. About the line, y equals 2. That changes everything. Tell me how that changes everything. Because one of the key questions you need to ask yourself when you're doing these problems is, do I have one function or 2? And right now, there's a giant part of your brain saying, well, of course there's 2 functions, because that's what they gave me. They gave me 2 y equations, yes?
I mean, that doesn't really change it because you're still going to have.
It absolutely changes it.
There's only one function. There's only one function.
Why?
Because you're revolving around y equals 2.
Because we're revolving around y equals 2.
But wouldn't the area still be the same? Because, I mean, the area of something isn't going to change just based on where you move it.
As though it's how you approach it.
You'd have to do that area.
Okay, what was the first thing I asked you to do on everything we've done today about the revolution problems? What did I ask you to think about before we did EMATH? What it was going to look like. What is this going to look like?
Like the little top.
It's going to look sort of like that witch hat version when we did a minute ago, isn't it? Sort of. But now it's not on the x-axis anymore. Because r represents the distance on the ones we've done so far from where? From the x-axis to the function, yes? We can't use that distance anymore, right? Because look at the point of the witch hat, which would be at the point, what's the coordinates of that point?
Pi halves 2.
Right, pi halves 2. Everybody see that? At pi halves 2, what is my radius? 0. If I use the function value there, what am I going to get? 2.
Okay.
Do you see it?
Can we just equalize it?
Okay, so here's what we're going to do. And these aren't that hard once you understand the distinction here. But if I'm now revolving around this line as opposed to my x-axis. And back to Mackie's point, because I think I heard you say this, correct me if I'm wrong, but I believe a minute ago you said, so we're going to have to go in terms of y? Did you say that? Okay, that wasn't a bad instinct, because that's obviously one of the changes you've had to make so far in the section, right, in the chapter. All right, but you're not going to go in terms of y, because this is how you decide. And I think I have this somewhere on your green or blue sheet, whichever one it is. When you are revolving around a line that is not one of the axes, how you set it up depends on which one it's parallel to. And here's how to think about it. What's the equation in terms of y of the x-axis? Y equals 0, right? Well, this is y equals 2. So this is like the x-axis moved up 2, right? So we're going to stay with x's. That's how I'm going to know to put everything in terms of x. Does that make sense? So then if they said revolving around the y-axis, and then we did a couple of y problems, and then they said now we're going to revolve the shape around y equals 4. I mean, x equals 4. Wouldn't that be you see what I'm saying? So it's the one it's parallel to. So this line of revolution, my center of revolution, is parallel to the x-axis, tells me we're going in x's. All right? So, but this is what you need to be thinking about. And I'm going to put a new color in here. Again, we'll go with pink in celebration of the day. I'm going to draw a radius in. And this will help you. If you just draw one radius and think about that radius. If I wanted to know that radius at that point, and let's just say for the sake of discussion that is pi 6. It's not a very good approximation of it, but just let's play it like it is. If I'm at pi 6, would the 2 times the sine of pi 6, 2 times the sine of pi 6, would that give me that radius?
No, we'll give you the minus.
What would give me that numeric value? Plus 2?
Area of the rectangle minus.
Times 2?
Minus.
Stop. Y'all are just like, y'all are acting like my 1B kids. Let me just spit out every math word I know and see if I can get the right one. Y is at the top minus bottom.
Because if you do the y equals 2 on the whole piece, and then you subtract it from the 2 sides.
Right. If I'm at y equals 2, first of all, on my line of revolution, what is y everywhere? 2, right? So if I just did that, my radius would be 2, and I'd get a cylinder, wouldn't I? Because now I'd be revolving the x-axis around that, right? Okay. But if I integrate just sine, or if I want just the sine's output there, that's going to give me the gap, which has nothing to do with my shape, right? Because, okay, we said this is going to look like the solid which hat, yes? Which means I'm going to use which method? The front or the back of that sheet? We're back on the front, aren't we? This is a disc with no hollowed out spot. So that means that I only need my radius, which is the distance from that line to here. All right? So let's come back to this point, because to me the endpoints make sense. What is the radius at the y-axis? 2. Right? Okay, so let's try it Kelsey's way. If I do 2 minus the sine of 2x, the sine of x, does that give me what I need there? What is the sine at the y-axis? The 2 sine x value. It's 0, right?
Yeah.
And 2 minus 0 gives me 2, right?
Yeah.
So then over here at this point, where we stopped our shape, which we agreed was pi halves 2, when I plug in pi halves, what is my, I still get 2, but I also get 2 from the sine, right? Because it's 2 sine x, you with me? So I get 2 minus 2, which is 0. That's my little tip to you, that once you think you've got it figured out, when you've moved away from one of the axes, check the ends and make sure they give you what you need. Because sometimes you'll get your thinking will be backwards. And here's another tip for you. Sometimes it would be y equals negative 2. Now that might mess with your head just a little bit, but here's what's cool. It still works just like it did on the front. All right? It's outer minus inner. Oh, not outer minus inner. It's just the outer radius squared because there is no inner if it's solid, right? Okay. But now, now we're not finding which formula to use. We're figuring out how to represent our radius, aren't we? Okay? So all this conversation we've been having has led us up to the idea that for our circular cross-section, so now you don't have to think about bases and heights and sides and all that diameter, whatever else you had, diagonal. Now it's just straight up, what is my radius?
2 minus 2.
And it's 2 minus 2 sine x. And that goes back to a little phrase I told you to get in your heads back in, I believe it was 8.2. Isn't that just top minus bottom? So when you feel trapped and you're panicking because you can't figure it out, go back to top minus bottom and see if that doesn't work for you. Verify it by checking your ends to make sure it works before you go on. All right, so now we're ready to set up our integral, aren't we? All right, so the volume of this shape equals pi.
Could you go and pull up the 2?
No, because it's squared.
I didn't hear what you said.
Did you just
I
drop
asked you
it?
to go ahead and pull up the 2 from the radius.
But
But you have to pull up.
So it'll be a 4.
Well, I mean, you could. It really isn't a bad idea because look what happens when I do that. If I pull that out, I get 2 times 1 minus sine x, right? Okay. Well, then when I come over here and I do my integral from where are we going? 0 to pi halves. And you see how it's almost like you did a lot of this without even feeling it, but we were already thinking about our limits of integration to get our thinking straight about what this shape was going to be and what my radius was. Okay? So we're going from 0 to pi halves. Everybody good on that one? Okay? And it's going to be our radius function squared. Okay? And in this instance, that's what we just found over there, right? So that's 2 times 1 minus sine x squared dx. And I didn't really need parentheses there either, but since I used them, I'll keep them. Actually, no. I have too many parentheses, actually. Let me go back, and this is going to mess me up, but I'm going to fix it. All right. There we go.
But when you have to put that in,
No,
outside.
you're right. I need a parenthesis here and a parenthesis there. That's what I actually need. Right? To the point about, because Becca's suggestion was a good one, but somebody said, well, we're going to square it. But what does that just mean for my next step? That 2 is just turned into a 4. So I'm going to go ahead and pull that out as 4 pi and forget about it. The sooner, anything you can push to the side and not have to deal with while you're integrating, the better off you're going to be. Okay, so this is the integral from 0 to pi halves of, so I'm just expanding 1 minus sine x squared. So that is 1 minus, jump in anytime, 2 sine x plus sine squared x dx.
Well, we got 2 sides.
You children. A minus b squared, let's have a little algebra 1 lesson here, is a squared minus 2ab plus b squared. My 1B class just took a test where that was one of the things being tested Tuesday. Actually, they did better than I thought they would, but I let them use some notes on it as training wheels. All right, so let's just talk through how you're going to integrate this and not do that, because again, we've done a lot of talking about that in the last couple of weeks. Obviously, 1 shouldn't be a problem, 2 sine x shouldn't be a problem. Agreed? What am I going to have to do when I get to sine squared x?
You'll have to use identity.
I have to use an identity that gets rid of the square, right?
Wouldn't you move the 1 and do the 1 plus sine squared x?
Absolutely, that would be a brilliant idea. Anytime you see a 1 and a cosine or sine squared, if they're the same sign, that's your out. I tell you what, that was so brilliant, Becca, we're going to go ahead and write it, because other people are like, what did Becca just say? 4 pi, integral of 0 to pi halves of, so we're going to keep the negative 2 sine x, right? And then we're going to add, but we're going to pause for a minute. Or was that a brilliant idea? Because I want to talk this through. Because y'all got to get to the point where you think about it. You don't want to ignore the fact that 1 plus sine squared is cosine squared.
Well, could you do u sub if you do no. I mean, you'd have to.
I want y'all to think this through.
But you could do you could do u sub, because then you could get your cosine.
Nope.
No, it would be cosine squared.
What's wrong with u sub? If I have sine or cosine, what else has to be there? The other one, right? And if I've only got one of them squared, u sub does not get me out. That's why the identities are important. That's a great identity to know because it comes in handy, but does that come in handy here?
I mean, you're gonna have to
Isn't it another?
Doesn't that take us kind of right back to where we were to start with? Because if I end up with cosine squared, I've eliminated the 1, but I like the 1. Why do I like the 1? Because its integral is x, yes? Okay, but I'm still stuck with what? A cosine squared, right?
Would you use the half angle formula? It's like 1 and out.
Okay, which one, how do I know which one I want to get? And I said this before Becca said that, and nobody responded, which told me you were just kind of in zombie mode. And I understand it's Friday, it's almost spring break, and we're tired, and yada, yada, yada. But you got to get your head in the game, because this is a very important set of thoughts to have. Okay? What's wrong with saying, let's replace 1 plus sine squared x, which excites me that you're seeing that now, because that's an important thing to watch for. But as soon as you get excited, you should immediately say, but I need to get rid of the square. It's the square that's the problem, right? Well, if I trade sine squared for cosine squared, I am no better off. In fact, you could argue you're worse off, right? I'd rather integrate sine than cosine. Because when it's cosine, sometimes I end up forgetting there's a negative involved. You with me? Okay, so back to the question. How do I decide which one? I'm looking for the identity that does not replace the squared trig thing with another squared trig thing, unless we're talking about tangent and secant squared, right? You with me? Okay, so I'm going to leave it at that. Good discussion, though, and that's what I was hoping for. All right, we're going to have to stop there.